Good afternoon, everyone. Thank you for joining us today. My name is Emily Silva, and I'm the NECAN coordinator. I'd like to welcome you to the 6th webinar in the NECAN Student and Early Career Scientist series, in which we are highlighting the work of students, PhD candidates, and early career scientists who are working on ocean and coastal acidification. The full schedule, along with past webinar recordings, can be found on the NECAN website, necan.org/student webinars. And announcements are made through our newsletter, so make sure you're signed up for that. A link to do so can be found right on the bottom of our homepage of necan.org. Throughout the presentation, if you have any questions, you can submit them through the questions tab on your GoToWebinar control panel, and we'll go through each during the Q&A session following the presentation. Today, we'll be hearing from Kelly McGarry from University of Connecticut at Avery Point on multiple linear regression models. Kelly is a PhD student in oceanography at UConn and is interested in understanding the processes that drive carbonate system variability in Northeast US shelf waters using models and observations. So with that, I'll hand things over to Kelly and she can take you through her presentation.
Thank you, Emily. How does it look?
So I can see your presenter mode, so you'll just have to switch that.
Okay.
Perfect.
Okay, great. Okay, thank you everyone for coming. Like Emily said, today I'm going to be talking about multiple linear regression models for estimating carbonate system conditions and exploring driving processes in the Northeast US. Anthropogenic emissions are increasing carbon dioxide in the atmosphere, shown here in red. And along with it, the PCO2 of seawater is also increasing, and it's shown here at the Open Ocean Station Aloha in teal. Ocean acidification changes seawater chemistry in multiple ways, and one indicator is the saturation state of aragonite, which expresses the thermodynamic tendency of calcium carbonate minerals in the form of aragonite to either precipitate or dissolve. That's plotted here in magenta, and as you can see, this value decreases with ocean acidification. In the coastal ocean, other processes interact with ocean acidification to determine the carbonate system conditions. On the Northeast US shelf, the Gulf Stream, which separates from the coast in the southern part of the region near Cape Hatteras, carries warm, salty water to the north. A southward flowing coastal current carries cool, fresh water southward. The wide shelf is highly productive, and so carbon dioxide is consumed by photosynthesis and produced in respiration. The result of all these processes working together has meant that the recent trend in aragonite saturation state on the Northeast shelf has not followed the global ocean acidification trend. So while dissolved inorganic carbon, which includes all of the species that carbon dioxide becomes when it dissolves in seawater, increased rapidly over the period from 2005 to 2015, and that's consistent with ocean acidification impacts. The aragonite saturation state was stagnant over this period. Similarly, the saturation state in the Gulf of Maine increased over this period. So here is plotted the anomaly compared to 2004. Both of these trends in aragonite saturation state were attributed to increased contribution of Gulf Stream waters on the shelf. The influence of those water masses is also apparent in the spatial distribution of carbonate system variables. So these are observations that have been collected in region-wide cruises every few years. The total alkalinity has a strong south to north gradient with lower values in the north. And that indicates lower buffering capacity in the north, which means that there's a greater change in PCO2 that results from a given change in DIC. DIC also decreases moving northward, however, the gradient is weaker. Aragonite saturation state is proportional, or it's inversely proportional to the DIC to total alkalinity ratio. And so it also has a sharp gradient along the coast, changing abruptly at Cape Hatteras. pH, on the other hand, does not show this latitudinal gradient. Observations of carbonate system conditions are especially limited in the subsurface, but they are also especially important here because that is where the lowest aragonite saturation states are observed, and conditions approach under saturation, which can be harmful to organisms. These conditions in the subsurface are also important because it's the habitat for calcifying species, including bivalves, sea scallop, softshell clam, and others. So observations of the carbonate system in the subsurface are limited, but all of the processes that I talked about as affecting carbonate system conditions not only affect the carbon variables, they also affect other variables. So water masses mixing together affect temperature and salinity. Air-sea gas exchange affects not only DIC but also oxygen. And those reactions that are the biological reactions that are happening affect oxygen and nitrate concentrations. So although the subsurface observations of total alkalinity and DIC are limited, we have more observations of other variables, including nitrate, many more observations of oxygen, and all of these data and more include observations of temperature and salinity. So we asked if we can take advantage of measurements of other variables that reflect the same processes that are affecting the carbonate system to estimate the carbonate system conditions. And we also asked what the equations tell us about driving processes so that we could get a better understanding of how these processes affect the carbonate system. To do this, we used observations collected on 3 regional cruises since 2007, which are shown on this map in orange. We fit multiple linear regression models that use combinations of temperature, salinity, oxygen, and nitrate to estimate total alkalinity, DIC, pH, and aragonite saturation state. So we were able to fit those because the carbon variables were measured on these cruises. The empirical model equations were selected based on the AIC score, which incorporates both the goodness of fit and the complexity of the model to determine which terms are worthwhile to include in the equation. So the results, this results in the set of equations shown here, where alphas are the coefficients and temperature, salinity, oxygen, and nitrate are denoted by T, S, O, and N. And the N subscript denotes that the values are normalized. So the mean is subtracted from the data and it's divided by the standard deviation. Normalization will allow us to compare the magnitude of the coefficients to determine which predictors are most important in each equation. We identified the overall best model for predicting each variable based on AIC score, and those are highlighted here. All of the best models for predicting each carbonate system parameter include all of the variables that we considered, temperature, salinity, oxygen, and nitrate, except for the model for total alkalinity, which just includes salinity and oxygen. So now to dive into the equations and see what they say about the processes, here the magnitude of the coefficients in each equation of the best models are depicted as a pie chart. So total alkalinity, you can see it's mostly explained by the salinity because it's mainly affected by mixing of water masses with different properties. Oxygen is a strong predictor of all of the other variables, which indicates that we need to account for biological activity to estimate those variables. And then temperature, while it's important for estimating DIC and aragonite saturation state, contributes little to the pH equation. And this is because the two effects of temperature on the carbonate system, one on the chemical speciation of DIC, and then the effect on air-sea gas exchange, compensate each other for pH, so that temperature is not a strong predictor of pH. These equations that we developed should reflect the processes specifically important to this region. And to test that, we calculated estimates of aragonite saturation state for the northeastern US using a model that was calibrated for the California current system. So our estimates are plotted in orange here, and we also plotted the model estimates using the model that was developed here specifically for the Northeast US. And you can see that the model for the California current system does not make good estimates of saturation state for the data from the Northeast US, because that's not what it was designed to do. And so what's different about these models that were developed for each region? So in the Northeast US, all of the models that we developed include salinity as a predictor, and it was not selected as a predictor for the models in the California current system. So this tells us that freshwater is an important driver of carbon chemistry in the Northeast US, while it's not in the California current system. Next, we asked what if we don't have the data for all of the predictors? How well can we still estimate each parameter with just a subset of those predictors? Since temperature and salinity are the most frequently measured predictors, we fit models that use only those. So here, the model estimate is plotted on the y-axis against the observation of the calibration data on the x-axis. And then R squared is displayed below each variable, and that describes the fraction of the variability in the observations that's explained by the empirical model. So you can see that the model using temperature and salinity explains nearly all of the variability in total alkalinity, which goes back to how total alkalinity is mostly controlled by the mixing of water masses with different properties. The temperature and salinity models explain a large fraction of the variability in DIC and aragonite saturation state, but they do not explain a large fraction of variability in pH, which also goes back to how temperature is not a good predictor of pH. Next, we added oxygen, and now using the model including oxygen, nearly all of the variability in DIC and aragonite saturation state is explained by the empirical model. Also, a much greater fraction of the variability in pH is explained. So, because this model that includes oxygen accounts for the effects of biological reactions. Finally, we compare the model that also includes nitrate. There was no model selected for total alkalinity, including nitrate, so nitrate doesn't contribute any more information about predicting total alkalinity. But for DIC saturation state and pH, there was a small improvement in the fraction of variability explained. This change was small because when we already were using oxygen as a predictor, that provided information about how much photosynthesis or respiration had occurred. And so nitrate as a predictor would provide mainly the same information. But still, nitrate improved the models because, as indicated by the AIC score. We evaluated the models using data from the most recent regional carbon cruise, and that is the data points shown in green on the map. And these points were not used to fit the models. So here again, the model estimate is on the y-axis, and then the observation is on the x-axis, except this time for data points that weren't used in calibration. And then the R squared for just the best model is shown for each parameter. And you can see that we are able to come up with good estimates that match the observations well for a data set outside of the calibration data set. The cruise used for evaluation also went farther into Long Island Sound than the calibration cruises had, so that allowed us to explore the model performance in a relatively fresh enclosed estuary. So here the residuals of aragonite saturation state are plotted, the estimate minus the observed. So values closer to 0 indicate better model performance. And they're plotted against salinity on the x-axis. So the low salinity values in Long Island Sound stand out to the left. So the model using temperature, salinity, and oxygen, which is plotted here in red, underestimates aragonite saturation state in Long Island Sound. Earlier, I showed that including nitrate only improved estimates in the overall data set slightly compared to the model that used oxygen. But we found that for these data in Long Island Sound, nitrate improved the estimates, and you could see that the green points at the low salinity values fall closer to the 0 line. This suggests that there's a process happening here to decouple oxygen and nitrate concentrations, and that's consistent with denitrification influencing aragonite saturation state in Long Island Sound. And we expect this to be the case in other estuaries, though we didn't have the data in this set to test that. So coming back to the questions that we set out to answer with the empirical model, can we use other variables to estimate carbonate system conditions? Yes, and we identified the best models that are recommended to use to estimate those carbonate system conditions. And what did the equations tell us about the driving processes? So we were able to look at the equation coefficients and determine which predictors are most important for estimating each variable. And the main points that came out of that was that freshwater is an important driver of carbonate chemistry specific to this region, that oxygen improves all models and it's really necessary for predicting pH, and that anaerobic respiration may be an important driver of carbonate chemistry in estuaries. One limitation of these empirical models is that they do not account for anthropogenic addition of carbon dioxide, so the results are only valid within about 10 years of the calibration period. To estimate conditions outside of that time frame, you would need to account for anthropogenic addition of carbon dioxide, and that's what we did in the application that I will talk about next. So this work was part of a special issue in the journal Elementa focused on the Gulf of Maine 2050. It started from a symposium back in 2019. And so physical projections that came out of that work are in the Brickman et al. Paper that I'll show, and then the biogeochemistry results are in the Sedlecki et al. Paper. And there are also some other papers about adaptation strategies and sea level rise and others that I would recommend checking out. Future simulations were run for the physical conditions in the Gulf of Maine. And so these were done by a regional ocean model that was forced by 3 different Earth system models, which are shown in each of the 3 columns. So those Earth system models are GFDL, IPSL, and HADGEM. And so here I'm showing the bottom conditions that were generated by this projection. So the color change at the top is the change in temperature, and you can see that all three of the simulations project warming, though to different degrees. The bottom panel shows the change in salinity. So in the first model, the salinity decreases, while in the following two, salinity increases. And so we wanted to estimate the future aragonite saturation state based on these physical models. So first, we applied the empirical model to the physical control simulation representing modern conditions. We compared the saturation state that was generated by the empirical model to a climatology from observations from the Gulf of Maine buoy D, so that's shown on the map, and the observations are the black boxes. So here I'll just discuss the green line, which was the ROMS model with the empirical biogeochemistry applied, and you can see that the empirical estimates replicate the observed seasonal cycle. To estimate the saturation state for future conditions, we calculated the DIC concentration in equilibrium with the atmosphere for the model calibration period. And then the ROMS projections were according to RCP 8.5. And so we calculated the DIC in equilibrium with the atmospheric concentration of carbon dioxide projected by that concentration pathway. And then we added the difference between those two equilibrium concentrations to the empirical model result to estimate the future values. So we applied the empirical model to the physical projection, and here is the resulting seasonal cycle in the same location as these observations. And so that's shown in the bottom panel. And again, you can focus on just the green lines, which is the empirical model projection. So as a part of this project, species impacts of ocean acidification were also reviewed, and a threshold of aragonite saturation state of 1.5 was identified as potentially harmful to organisms. So here, that threshold is plotted in yellow. And you can see that the ROMS model using the empirical biogeochemistry projects persistent conditions below that threshold for the first 5 months of the year in this location. It also projects a shift in the seasonality of aragonite saturation state, with the maximum values occurring in September instead of August as they were in the control. And so here the spatial distribution of the projected future conditions are plotted. And we calculated an acidification intensity score using that threshold of 1.5. So the intensity incorporates both the amount of time that the conditions were below that threshold with the magnitude that it exceeds that threshold by. And so the top panel is the surface and the bottom panel are the bottom conditions. You could see that in the control and in the future, the most intense ocean acidification conditions are in the southwestern Gulf of Maine. And then Georges Bank experiences the least intense conditions and actually stays above the threshold in one of the models in the HADGEM model. What also stands out in this figure is the difference among the three simulations. So again, that HADGEM model that I pointed out, much of the Gulf of Maine remains above the threshold value of 1.5, but not in the other two models. And the HADGEM model was the one that projected the greatest amount of warming. So the warming is compensating the ocean acidification signal in the future aragonite saturation state. And so from that, you can see that the future carbonate system conditions depend not only on the carbon dioxide emissions, but also on the physical future. So the limitation of using the empirical model to make future projections was that it couldn't include biogeochemical feedbacks like possible changes in productivity rates or sediment respiration. So we also compared it to a biogeochemical model that was run for the Gulf of St. Lawrence. So GSBM is the Gulf of St. Lawrence biogeochemical model with dynamic biogeochemistry. And we found that the changes that were projected by both of the models were very different, where the empirical model projected smaller changes in saturation state than the dynamic model. However, the final values are more similar, which means that there is more of a disagreement in the initial saturation state. The GSBM model had the benefit of dynamic biogeochemistry, so it could simulate those biogeochemical feedbacks, but it also simulated a constant decline in aragonite saturation state, which we know is not consistent with the observations that I mentioned earlier and other observations provided in this paper, where you could see an increasing trend, at least for a part of that period. And so, though that model has the benefit of dynamic biogeochemistry, it may not capture the circulation influences on carbon chemistry because its domain does not include the path of the Gulf Stream. So it can include physical biases from the global models. The ROMS model, on the other hand, extends from the Gulf of Mexico, including the path of the Gulf Stream. So one of the models used in this study had the benefit of dynamic biogeochemistry, while the other may have had more realistic physics. So to get the best possible projections, we would want to have both. So concluding back to the empirical model equations, if you have observations of temperature, salinity, oxygen, and possibly nitrate, depending on where, whether it's in an estuary type system or on the shelf, you can apply the models provided in that paper and estimate carbonate system parameters, and I'd like to hear how that goes. And then in conclusion, regarding the Gulf of Maine projections, the models with the most pronounced warming experience the largest masking of the ocean acidification signal. So better constraints on the fate of the Gulf Stream are a high priority to reduce uncertainty. And future work needs to focus on potential biogeochemical feedbacks. And that is all I have. I know I went through it fast.
That was great, Kelly. Thank you. So we actually do have one question in already. So is RCP 8.5 business as usual scenario the most appropriate model to use, knowing that global actions are moving forward to mitigate climate change? Or have you thought of using a lesser model like 6.0?
Yeah, that's a really good point. So for this particular application, I believe we matched up with what the physical conditions had used, the physical simulations that we were working with, but I think it's definitely important to, it'll be important to use more realistic carbon dioxide concentrations for going forward with more dynamic modeling.
So that was the only question we have so far. So I'd like to encourage people to submit a question through the questions tab on the GoToWebinar control panel. I can give another minute or so. If not, then we can say that was a great presentation and thank you very much, Kelly. But let's give it another minute. Let's let people submit a question if they would like to. Well, I don't see any of them coming in. Oh, somebody said you did a great job. Have you examined perhaps deriving a separate algorithm for Long Island Sound?
Yeah, so I haven't, because I'm interested in sort of a shelf-wide, like region-wide application and simulation, but I think that it looks like the same empirical model could possibly apply as long as you're using all of those predictor variables, including nitrate, which would be good. But I think it might be worthwhile if you're focused on working in Long Island Sound to determine if those variables relate to each other in a different way.
Are there future cruises where you'll be able to retest the estuary predictions that you found in Western Long Island Sound?
That's a good question. I don't know what the cruise track looks like for the next East Coast ocean acidification cruise, but so that was the most recent one where they decided to take that cruise track. So it would make sense if that was sort of an update and they're planning to do that again.
Okay, well, it looks like that's our last question.
Okay.
So that would conclude our webinar for today. This has been recorded and will go up on the NECAN website early next week. So check back there. But if you are subscribed to the NECAN newsletter, you will get a notification of when that recording is available. The next scheduled webinar is on Thursday, June 3rd at 1 p.m. and is the last in the series, so don't miss it. The registration link is currently up on the NECAN website, necan.org/studentwebinars. And then more information on the topic and the title and abstract will be shared soon. I also encourage everyone to request an account on the Ocean Acidification Information Exchange if you don't have one already. It's a great resource for information on ocean acidification, and you can get notifications for webinars and other events and engage in conversation with others. So again, thank you so much, Kelly, and thank you everyone else for joining us today.
Thank you.